In this lecture, we will show that a Möbius transformation on the extended complex plane maps lines and circles surjectively onto lines or circles. Lines and circles are collectively referred to as clines, and so according to the theorem that we will prove, Möbius transformations will map a cline onto another cline. Let f be a Möbius transformation so that f of z can be written as the quantity az plus b divided by the quantity cz plus d, where a, b, c, and d are complex numbers, with ad minus bc not equal to 0. If c equals 0, so that both a and d are non-zero, then f of z is equal to a over d times z plus b over a. And if c is non-zero, f of z is equal to a over c plus the fraction bc minus ad divided by c squared times the reciprocal of z plus d over c. In the case when c equals 0, f is made up of a translation that we will call t sub b over a. T sub b over a of z equals z plus b over a. T sub b over a is composed with what we call a rotation dash dilation slash contraction. We call this rdc sub a over d, where rdc sub a over d of z is a over d times z. We can write a over d as the absolute value of a over d times e raised to the power I times alpha, where alpha is an argument of a over d. Since a and d are both non-zero, the absolute value of a over d is greater than 0. So multiplication by the absolute value of a over d is a contraction if the absolute value of a over d is less than 1, and is a dilation if the absolute value of a over d is greater than 1. We get only the identity map if the absolute value of a over d is equal to 1. Multiplying z by e to the power I times alpha rotates z counterclockwise around the origin by the angle alpha. And so multiplication by a over d is the composition of a rotation with a dilation or contraction. If c is not equal to 0, then f of z can be decomposed in the following way. We start with a translation. We call this translation t sub d over c. T sub d over c of z is z plus d over c. Then we have the reciprocal map. R of z equals 1 over z. bc minus ad is non-zero, since it is the negative of the discriminant ad minus bc, and ad minus bc is non-zero. C squared is also non-zero, so that bc minus ad divided by c squared is non-zero. And so multiplication by the fraction bc minus ad divided by c squared is a rotation dash dilation slash contraction, which we call rdc sub 1. Lastly, we have the translation t sub a over c. T sub a over c of z equals z plus a over c. If we show that each of these transformations maps clines onto clines, then we will have proven the theorem that Möbius transformations map clines onto clines. In the video Möbius transformations, the reciprocal map, lines and circles, we had shown that the reciprocal map maps clines onto clines. We refer the viewer to this video for the proof that the reciprocal map maps clines onto clines. We are including the link to this video in the description of this lecture. Rotations and translations are examples of what are called Euclidean isometries, and so they preserve distances and angles. They only move circles and lines around without changing their shapes. Rotations are also surjective, since each rotation is invertible by the application of the reverse rotation. Likewise, translations are invertible and are therefore surjective. And so rotations and translations map clines surjectively onto clines. Now that we know rotations map clines onto clines, we have only to deal with dilations and contractions. Let z be equal to x plus y times I, where x and y are real numbers. Let D be either a dilation or contraction, so that d of z equals u times z, where u is some positive real number. If u is positive, then u times a large number will still be a large number, and so we have d of infinity as infinity. D is a dilation if u is greater than 1. D is a contraction if u is less than 1. If u equals 1, then D is the identity map, so that u equals 1 is a trivial case. D is also surjective, because D inverse exists. The viewer can check as an exercise that D inverse of z is just 1 over u times z, so that the inverse of a dilation is a contraction, and the inverse of a contraction is a dilation. U times z is equal to u times x plus u times y times I. We set this equal to z prime, which we write as x prime plus y prime times I, where x prime and y prime are real numbers. We first examine what D does to a line. Let L be the line given by the equation ax plus by equals c, where a and b are not both 0, and a, b, and c are real numbers. Replacing x and y by x prime over u and y prime over u respectively, we have a times x prime over u plus b times y prime over u equals c, or that a times x prime plus by prime equals c times u. This is the equation of a line passing through the point at x prime, y prime. We call this line L prime. Every point z prime on L prime has a corresponding point z or z prime over u on line L, such that d of z equals z prime, and so the transformation D maps line L surjectively onto line L prime. Let us now examine what the mapping D does to a circle. We take circle Q, whose center is at hk and whose radius is r. If z is on circle Q, then it satisfies the equation x minus h quantity squared plus y minus k quantity squared equals r squared. X and y are equal to x prime over u and y prime over u respectively. We multiply by u squared. We get x prime minus uh quantity squared plus y prime minus uk quantity squared equals the square of the product of u and r. This is an equation of the circle whose center is at uk and whose radius is u times r. We call this circle Q prime. Every point z prime this time on circle Q prime has the corresponding point z, which is equal to z prime over u on circle Q, such that d of z equals z prime. And so dilations and contractions map circles onto circles. Combining this result with the result for lines, we have that dilations and contractions map clines onto clines. Now that we have shown that each of these transformations map clines onto clines, we therefore conclude that Möbius transformations map clines surjectively onto clines.